All right. Good afternoon, everyone, and welcome to the Phoenix LiDAR Systems November 2021 webinar. Today's topic is assessing entry-level LiDAR systems for 2022 and taking a deep dive into data comparisons and what they actually mean. And with that said, I'll pass it off to my colleague Conrad to get us started.
All right, thanks, Terry. Hi, everyone. Phoenix LiDAR specializes in custom mapping solutions. In addition to hardware, we build support systems that include methodologies, user-friendly controls, processing software, and technical guidance. So it's a lot more comprehensive than just the payload. At PLS, we're always striving to build more complete systems, and that has led us to be pioneers of many advancements. In the last webinar we hosted, we shared our real-time mission guidance software, which is just the latest in our list of accomplishments that aim at pushing the technology further. Today's webinar is going to focus on getting a clear picture of the similarities and differences that you'll find in our more entry-level UAV LiDAR options. My name is Conrad Quinterno, the post-processing manager at PLS, and I'm joined by Terry Owens, who introduced us. We'll start the webinar by discussing the attributes that are commonly used to differentiate scanner or dataset quality and what factors significantly affect them. Then we'll have a data review where we perform a side-by-side comparison of the Recon A, the RECON-XT, and the miniRanger. Afterwards, we'll review it all and talk about what you should consider when making a decision. Let's begin by reviewing data quality attributes. We're asking the question here of how do we evaluate systems and their data? The first thing that might come to mind is quote unquote accuracy. We need to be a lot more specific than that. So we'll discuss three metrics that are all at play: precision, relative accuracy, and absolute accuracy. Another approach to thinking about data quality is from an application standpoint, and based on the question of what can this data do for me and how well can it do it? That leads us to consider things like data resolution and capabilities of a scanner to collect certain targets. In addition to knowing the quality attributes, it's also very helpful to understand the factors that affect them. This really allows us to gain a more comprehensive understanding of these differentiators. First, and possibly most importantly, is precision. This is the ability of a scanner to make consistent measurements on a hard surface target from within a single pass. You can think of this as the fuzziness of a flat surface as measured within one flight line's data. Precision is a very apparent property of the data set when you start visualizing and inspecting carefully. High precision data enables us to effectively have a higher resolution or sharpness. And this attribute cannot be discounted, especially when we're measuring or modeling features. To analyze the precision of a data set, most users start with a visual analysis. Some also take a more thorough approach that might include a raster-based range analysis that yields some statistical results. If we're producing data to meet an industry standard like an ASPRS accuracy class or a USGS quality level, then quantifying precision is a necessity. Relative accuracy is how well our overlapping passes of data match each other. Relative accuracy is usually measured by comparing surfaces created by different flight lines in areas of overlap on single return hard target areas where the terrain is not too steep. You'll usually see a magnitude of mismatch or an RMS DZ value given for a data set that conveys how things are aligning swath to swath. Absolute accuracy is what you most often heard about. It's the pass or fail spec in the service world. Absolute accuracy is a measure of how well your data matches some quote unquote true or accepted values. In the UAS and airborne remote sensing world, LiDAR is typically considered an elevation data source. and thus absolute accuracy is evaluated in the vertical direction only. Absolute accuracy can be measured against a final results LiDAR dataset or a derived product like a DEM, and some standards actually call for both measurements. The common way of conveying this type of accuracy is RMSEZ, or root mean square of error in the Z direction. Beyond the accuracy attributes, there are quality metrics that are a little more application-centric. Data density is often discussed. The number of points that a scanner measures per surface area is definitely a consideration. Higher density means more likelihood of canopy penetration and better resolution, at least to a certain level. There seems to be a point of diminishing return where point density for mapping is largely related to precision. It's actually pretty similar to a discussion about megapixels versus resolving power of a camera array. So just because a scanner can measure 1,000 points in a square meter does not necessarily mean that you'll be able to measure 1 centimeter sized features. The last consideration that we'll discuss is feature detection. Various properties of a scanner can influence its ability to map specific targets. Penetrating through a canopy layer or measuring small utility infrastructure are the more common type of features that a scanner may or may not be able to acquire. A directly related quality metric is range performance, or what is the maximum range at which a scanner can measure a given target. To further our understanding of these quality metrics that we've discussed, it's very useful to have a grasp on the quality factors that impact them. 3 metrics often lumped into the statement of accuracy are actually influenced by a range of different factors. Precision, for example, is highly impacted by the intrinsic properties of a scanner and the target that it's interacting with. On the other side of things, the relative and absolute accuracy are massively impacted by navigation data, which software was utilized, and what workflow is employed. So let's break these factors into a few categories. In the first category, we have the laser's intrinsic quality and the pulse's interaction with the target. Essentially, these are what dictate the photon budget of a pulse. The output energy and how beam divergence spreads that, in tandem with how reflective a surface is, the incident angle, and the measurement range, all impact the signal to noise ratio and determine which targets can be measured and how precisely those measurements can be made. A laser's intrinsic quality is also impacted by its ability to encode angles and make sure that these range measurements are pointing in exactly the right direction. The second category is much more on the side of data processing and how workflows are carried out. Differing processing workflows can yield drastically different relative and absolute accuracy results. One major example of this is how were reference station coordinates determined? Was OPUS used? Are these average coordinates? Or is this a known point that will allow you to effortlessly tie your data into an existing network? The point here is that there is a significant amount of ambiguity with respect to data processing that has a major impact on what accuracies can be achieved. In the example on the right, we're showing how 3 different surfaces could be constructed from the same set of LiDAR points, each resulting in some level of over or underestimation of error when compared to these true checkpoints. Let's take a look at data from 3 flights to see some differentiating attributes between the Recon A, the RECON-XT, and the miniRanger. On my screen in Spatial Explorer, we have 3 clouds, one from each sensor. The clouds for each sensor were collected during missions flown at 60 meters above ground level using north-south passes with one east-to-west perpendicular line and all flown at 6 meters per second. All data were processed first using a tightly coupled trajectory and boresight values applied to build a cloud. Then each cloud was fully optimized for relative and absolute accuracy using a tie line matching and optimization process. In Spatial Explorer, you can also see that there are check and control points loaded. Of the 46 total points, 4 of them are control points that we've used to remove vertical bias from each project. 24 of them are checkpoints that we use for validating accuracy statistically, and the remainder are unused points on curb edges or above ground objects. So let's begin by inspecting our absolute accuracy. We'll begin by doing a visual analysis to see how each point cloud matches with our surveyed checkpoints. We'll start with the Recon A. I'll zoom in near one of our checkpoints, and we'll take a cross-section profile. And view this profile in a new viewing window. We zoom in on checkpoint 10. In our cross-section, you can see that it's very nicely aligned with the point cloud, or rather the point cloud is nicely aligned with checkpoint 10. So our initial gut reaction is that the Recon A dataset has good absolute accuracy. Let's move on to get a visual understanding of the RECON-XT data. In that same profile, we can see that the RECON-XT data is also nicely aligned with checkpoint 10. Let's see the miniRanger. And it's no surprise that also the miniRanger is really nicely aligned. So the data checks out visually just based on a spot check, but what we really want to see is statistically how well our overall mission is aligning with our checkpoints. For this, let's review accuracy reports that were generated from Spatial Explorer. So we'll start with the Recon A. For absolute accuracy, we create a ground model for the entire mission, and then create a tin from that ground model, and at each checkpoint location, interpolate values from the tin to derive our laser Z values. Then we take the difference between the surveyed value and the laser Z value to get a difference, and we summarize that as RMS error Z. This is the metric that explains the overall absolute accuracy of our data set. So for the Recon A, you can see that it's really nicely aligned with our surveyed truth points. The RECON-XT, using 24 independent checkpoints, we can see that this data set is also very nicely aligned. And for the miniRanger, this one also is right in that realm of 1 to 2 centimeters of accuracy compared to surveyed checkpoints. So the absolute accuracy statistical analysis is definitely supported by our visual analysis. It's important to do both. Ultimately, the statistics are what rules, but you can see that they follow each other pretty closely. So let's move on to relative accuracy, where we will begin with an initial visual assessment and then move on to a statistical analysis. Let's start with the Recon A. Let's change the symbology to color the data by GPS time rather than by elevation. This will help us see each discrete flight line. We'll start by looking at our profile view. You can see that the different colors symbolizing different flight lines show that there's a really nice mixing of the different passes. So our initial impression here is that the relative accuracy is good. Of course, this is just one area that we've spot checked. If you zoom out a little bit on the top-down perspective, you can see that areas where one color dominates generally mean that the data from that flight line is above the data from the other flight lines. So this can also be a clue into the relative accuracy, and it can help you see patterns in the data. So where we can see the edges of this perpendicular flight line where the red points are above all of the other flight lines, that's some indication that the relative accuracy might not be spot on there, or there might be something else going on. Let's take a cross section and get a little bit of a closer look. So if we zoom in to this area where the red flight lines seem to be above the others, you can see that it's still matching the green pretty well, but maybe we're actually seeing the effects of imprecision rather than relative accuracy. Overall, though, the flight lines seem to be matching each other really nicely. Let's move on to checking out the RECON-XT. Again, we'll switch the symbology of this data set to show GPS time rather than elevation. Looking at the RECON-XT, we can see that the different flight lines, symbolized as different colors, are blending together very nicely. It's pretty hard to distinguish whether one of them is above or below the neighboring flight lines. We can also see in the top-down perspective that the points seem to be blending together really nicely. There's not many areas where one color dominates, and that's a good indication that our relative accuracy is in good shape. And now we'll move on to the miniRanger, and we'll change the symbology of the miniRanger so that we're looking at GPS time instead of elevation. Our miniRanger data also appears to have quite good relative accuracy. We can see in our profile view that the flight lines are matching each other very well, and in our top-down view that everything also seems to be blended quite nicely. Looking at the relative accuracy reports from Spatial Explorer, let's start with the Recon A. So relative accuracy metrics are created by creating a ground surface per flight line and then comparing ground points from other flight lines to that surface. That gives us the delta Z values that we can use to create a summary statistic of the RMS delta Z per mission. So for this Recon A mission, our relative mismatch between flight lines is just over 2.5 centimeters. That's pretty good. That's a good indication that our data set has been calibrated. We can move on to the RECON-XT and look at similar statistics that were created by this data set. Here our RMS DZ value for our data set is just under 2 centimeters, so that's quite good matching between our flight lines. And finally, we'll take a look at the miniRanger. In this case, we're at just over 2 centimeters. All of these relative accuracy metrics support what we were seeing visually in the data. They're all high quality, and they all are a good indication that our data set has been calibrated sufficiently well. All right, now let's move on to intra-swath precision, or hard surface repeatability. This is really one of the key differentiators between scanners. We'll start with the Recon A. When we're checking on precision visually, it's extremely important that we're looking at hard surfaces and that we're only really focusing on points from single flight lines. It's also important to make sure that the targets you're looking at aren't extremely low or high reflectivity at the laser's wavelength. So if we look at this sidewalk, we can see there are a few flight lines here. Let me adjust this GPS time so we get a little bit better differentiation amongst the different flight lines. I'll use my measurement tool and start measuring this red flight line. It looks like the height here is about 7 centimeters. The red flight line in this location's closer to 5 or 6. If we measure the green, we're going to be kind of in that same realm, 6-7 centimeters-ish. So this gives us a nice gut feeling of what the precision or the single pass repeatability on a hard surface is going to be. Let's look at the RECON-XT next. First, we'll measure this red flight line here. It looks like about 2.5, maybe including this outlier up to 4. There's a lighter kind of a cyan color here that looks like about 3.5 centimeters. Darker blue one here, about 3.5. And finally, let's look at the miniRanger. First thing that's pretty obvious is that the miniRanger's data is a lot less dense per flight line than the other two. So measuring the precision here is going to be a little more subjective. First measurement about 2.5 centimeters. This scan line looks like about 1.5 centimeters. We can measure, there's some blue points here. That's about 1.6, looking at those light blue points. So it looks like around 2 centimeters for the miniRanger. That gives us an initial impression of the precision. This is commonly the quality that you're going to be noticing when you're looking at point clouds a lot. It impacts your ability to measure features. It impacts kind of the crispness and the resolution of the features that you're looking at. In order to get a more thorough understanding of precision, we really need a more robust methodology. And so what we've done is find an area of relatively flat, hard surface, and we chose this wide open parking lot, exported data from the parking lot for each scanner, and then per flight line per scanner created rasters with 50 centimeter cell edges and performed a range analysis according to the USGS methodology to determine the precision of each scanner. One of the really important criteria is that we're selecting an area that has data from multiple flight lines, and the purpose of that is so that we can have different scan angles and different incident angles included. We don't want to just look at points at nadir or just look at points at the scan line edges, because the difference can be quite drastic. So let's take a look at those results. When we analyze multiple flight lines in that parking lot area, we can determine that the RMS of the elevation ranges for the entire data set works out to about just under 6.5 centimeters of precision. So that means roughly 6.5 centimeters of thickness. If we look at the RECON-XT results, for this data set, we get just about 3 centimeters total of statistical precision. And then if we look at the miniRanger, we're at a little over 1.5 centimeters. These numbers pretty closely represent what we were able to measure by hand, and they give us a pretty firm comparison between the scanners. The next quality attribute that we're going to look at is vegetation penetration. To compare the scanners, we've selected an area with some pretty dense vegetation and isolated points from the single east to west pass for each scanner. First, taking a look at the Recon A data, let's turn off the points that are not ground points. So now we're left with what we were able to map as ground. The sheer quantity of ground points isn't really what's important here. What we want to know is how well can this scanner map the details of the terrain. So to quantify this, we're going to only consider areas of ground that meet the minimum point spacing requirements for 1 foot contour intervals. That means that we're going to take any points here that are more than 70 centimeters away from their nearest neighbor and discount them as viable ground points. Now we're left with only reasonably high confidence areas that have been mapped on the ground. We can perform this same routine on all three of the scanners. It's important for me to mention that these three missions were not collected on the same day, so it is a bit of an imperfect comparison, but we did select data from flight lines that were flown at nearly identical locations. We tried to make it as fair as we possibly can. And from here, we can export this data as rasters and evaluate how many raster cells have valid ground points within them. That gives us a ratio of area mapped versus area not mapped. Let's take a look at what this 2D exported raster data looks like. You can see areas where there are white pixels, that's where the ground has been mapped, and areas where the pixels are black is where there's no ground coverage. This is the Recon A we're looking at here, and the percentage covered is 44%. The RECON-XT in this area has 66% covered, and the miniRanger has 51% covered. This shows us that each of these scanners can map the ground beneath vegetation from a single pass, but there are differences, most likely caused by differing pulse rates and point spacing, and also different beam divergence per each laser. The final question we'll ask today is, can each of these scanners map utility infrastructure? So let's go back to Spatial Explorer and move our map frame over to the west a little bit where there is a little power line corridor. We'll draw a cross section and just take a quick peek at what each of these scanners captured. In this location, it looks like the miniRanger's got the main wires, a shield wire up top, and another smaller cable below. The RECON-XT has mapped everything here with pretty high density on the wires and nice definition on the pole. And finally, the Recon A. The Recon A looks like it's got some points on this pole, probably enough to identify its location, but not really given much shape to it. It's also captured all the wires, although they are a little less precisely defined than in the other two scanners. So from 60 meters, it looks like all three of these are perfectly capable of doing utility infrastructure mapping. Thank you all so much for taking the time to dive into this data and compare and contrast these three scanners with me.
Thanks for that in-depth comparison of the data, Conrad. Now let's do a quick summary of the results. As we can see, the payloads were all flown at the same height and speed for fair comparison. The FOV of the Recon A is 70 degrees fixed downward, while the XT and miniRanger are 360 scanners, which we set to 90 degrees in aerial scanning applications. This does give the XT and the Mini more multi-platform flexibility. For accuracy, we can see that precision was best on the miniRanger, with the XT showing about double the thickness and the A about 4 times the thickness. As Conrad showed us, relative and absolute accuracy are heavily dependent on the software workflow and system calibration. And these are the figures you'll usually see advertised by companies, and they are case-by-case dependent. When looking at accuracies, the term survey grade is often thrown around in this industry, and what people are typically referring to is a 3 centimeter absolute accuracy to GCPs, or about 1/10 of a foot. By that metric, it would appear that the Recon A is a survey grade system, and some companies do market it as this way, but you can't discount the fact, as Conrad said, that precision does have some effect on the overall quality of the sensor. A density analysis shows us that the A has a very high density. The XT is fairly high, and the Mini does have a bit less density. Now, depending on your profession, less density might actually be preferred. And I'm sure some of the LiDAR experienced surveyors and engineers actually enjoy having a data set that is a bit less dense, as they normally do have to decimate the point cloud to work with it in different programs anyways. If we compare the spot size, which is beam divergence, projected at 60 meters in this case. The Recon A has the highest beam divergence, XT is in the middle, and the miniRanger has the tightest beam divergence. Basically, less beam divergence means better precision, which makes sense comparing the other metrics. Ground coverage shows the XT having the best, trailed by the Mini and then the A. And now some of you might be wondering why the Mini has better coverage than the A, even though the A has much higher density. And this is directly related to the beam divergence. Now, since the Mini has less divergence, the allowed photon budget is more effective at finding those gaps in the canopy. And lastly, as we saw in the video, all of these systems we would consider suitable for utility infrastructure at 60 meters. But this is where the A starts to cap out on range. The XT and the Mini are both capable of flying a bit higher and maintaining full coverage of the poles and the lines. Now, there are three main things to take into consideration when evaluating a LiDAR system, especially an entry-level system like these. Will it work for what I need? Is it within the financial means of the company? Am I going to be able to make money with this asset, or am I buying a very entry-level LiDAR system to have LiDAR in the portfolio? Some questions you should also be asking yourself are, how is this going to be implemented into my current business model? Which members of staff do I want trained on it, and so on and so forth. And we're here to help answer those questions. Something I hope this webinar made clear is that we're not talking down these entry-level products. There's a reason we hold them in our portfolio, and that is because all of these LiDAR sensors are fantastic tools for different jobs. While some companies only sell entry-level systems or only sell the very high end of products, Phoenix LiDAR is in the unique position where we do have the entire range of sensors in our portfolio and can make unbiased recommendations based on your use case. And that being said, as you can see, there are a lot of complex choices and sometimes trade-offs when it comes to selecting the LiDAR payload, which is why consulting an industry professional is always the best option. Our sales and engineering teams have the proper experience to make sure you get the right tech at the right price. And thank you again to everyone who is watching the webinar live or on YouTube after the fact. I hope you gained some value from this and are more educated heading into the LiDAR market. And with that, we will open up to Q&A. All right, Conrad, for the first question we have, why does it make sense to buy a Ranger LR UAV system over a Recon A or RECON-XT for linear transmission line mapping?
Well, I think that the precision of the data is the number one differentiator that you're going to notice. I think probably the range capability is slightly better. You might be able to fly at the max UAV ceiling more confidently. You will be able to fly at the max UAV ceiling more confidently with the Ranger than with either of the Recon options, just because it has a better ranging ability. I think those are probably the two biggest differentiators.
Fantastic. Yeah, and to add on to that, just to emphasize what Conrad said, the A and the XT are good for linear transmission line mapping. Something to take into consideration is system efficiencies as well. With the A and the XT, of course, you're going to be limited to those lower altitudes and therefore drone collection. So for small areas of transmission line, maybe that makes sense. But if you're looking to do more collection at a higher altitude, then efficiency does come into play, and a Ranger system does make sense at that point. We got another question. I don't know, Ben, if you're on the line, if you want to take this one. Which one is the best sensor for vegetation penetration purposes?
Can you hear me, Terry?
Yes.
Cool. I would say Ranger XL. Essentially, the heavier and the more power you have, the more you're going to penetrate vegetation, and it's really also a function of beam divergence. So I would probably go with a Mini 3 if that was my goal. If we're limited to the three sensors that were discussed. But yeah, you can clearly see that once beam divergence shrinks, you have a better chance of getting through to the ground.
Thank you, Ben. Conrad, have another one for you. On the left side panel of the software tool, and they're referring to Spatial Explorer Pro, there are what seems to be data sources. One is labeled as reference stations. What are those?
Oh, that would be in the case where we're processing our navigation data through Spatial Explorer, and we would be uploading our static reference station for processing our trajectory. We weren't using it in this case, but that's what it would be used for.
Very good. Right, the Q&A we will still leave open for another couple of minutes, but I think that's the end of the questions that we have in the queue thus far. Thank you again, everyone, for attending. And I think we're going to wrap it up there. So everyone have a great rest of the day. Thank you for coming to the webinar, and we'll see you next time.